This video is the 2017 higher level section A. This video will look at A1 and A2. There's a link in the description for A3 and A4. So question A1 is an axonometric projection question. The image below shows a Bluetooth mini speaker. The speaker is based on a cube with its face is cut as shown. The drawing on the right shows an incomplete axonometric projection of a similar cube using the axonometric axis method. Planes of reference are also included. The elevation and plan, so I've got an elevation up over here, plan down here, are shown in the required positions with lines drawn on three visible faces. So we've got the top face here, which is visible. This is one side face and another side face here. Part A of this question is to complete the axonometric projections of the cube and the given lines, and part B is to determine the true angle between the lines AB and CD. So that'll be on this face up here, so we'll be looking for that in a while. So starting out, I'm going to draw just the basic outline of the box first, the cube. So sliding set squares. So projecting all of these lines up, just going to extend this one on further. And that will allow me then to bring the rest of these lines down. So we have this corner is going to be this one up here, and this corner is this one back up here at the back. So taking each line, this line projects down like this way. That gives me the top corner of the cube. So we can darken in this bit of a line here. Here and here, and down the side as well. So we get that completes the cube, the basic shape of the cube. So I'm going to do each face one at a time. So they have line C and D here first on this one, so I'm going to complete that face with line AB. So taking point A, so all our lines are going to come parallel to the red ones that are already projected down. This one comes down along. Point on the top surface, so that's on the top surface of this face, so it's up there. B is on the bottom surface, bottom edge of that surface, so this is B and this is A up here. So we can join these two together. That gives me the line AB in the axonometric view. What I have next then is we'll do the top. There's three lines up on top of this. This point continues on from here, so that's point B, or sorry, point A. That's the only one with a label on it, so we're going to find the other points then. So each of these points is projected from the plan up into the axonometric view. So I already have point A there on the side, so let's find the opposite one of that. So extending that line across, it's here, it's on this edge, which is this edge, so we're going to take this point, project it up until it intersects that edge. That gives me this line here. Pick another line, let's take this line here, this one. So taking this point, it's on the front edge, top edge, so it's going to be along here. So let's find that up in the elevation, or the axonometric view. So that's this point. This line here is the back edge, that's this one. So taking that same line, projecting that up. That gives me this point. I can join those two together. And finally there's this line, so this third line, this one. I already have one of those points. It appears to be in line with this here, so we can extend that on further. That gives us the point at the back. And this line again, it's on the same edge as this one was here. This point, taking that one up there, so I can take from this point across to here, and that's the top surface. The final surface then is the front face. That's this one down here. We can't really see it. Well, we can just see an edge of it here, but we can see most of it on this, or all of it here. Okay, so it's going from this line over here, this bit. That's how much we can see there. Okay, so there's two lines on this. We have this point here, D already. This point is going to be this one up here, so we're just looking for 2 points, this one and this one. So I'm going to do the line that joins to D first, so it's this line along here. It's on the vertical edge, so this line here. I'm going to project that down until it intersects with this one. That's this point, so we can join that one up now again. And one more line to do to complete part A. So that's this line down here at the bottom. So they happen to kind of go in line with each other. So that can go further till it breaks through the bottom. So this is on the bottom edge. So this is that same bottom edge. They're going to join up. And that completes the section A, completing the axonometric projection of the cube. Part B of this question is to determine the true angle between the lines AB and CD. So AB and CD are on this face here. We can't see the true angle here because we need to see a true shape of it first. To get a true shape, you need to have an edge view of something. I have an edge view of this here, so we're going to look in perpendicular to that. We're going to project along here, looking in perpendicular, taking our heights from the elevation. So this will be our heights from the elevation, and we'll go from there. So first off, projecting off perpendicular to this. And I'm going to draw an x1, y1 line out here. So we're essentially drawing an auxiliary elevation. This is a plan. I'm going to draw an elevation off of that. I'm going to take heights. So this point here will be this height up here. So I'm going to measure whatever height that is in the elevation. Alright, and this allows us to draw the cube. So this is an auxiliary elevation of the cube, showing us just the face that contains the sides A, B, C, D. So this is an edge view of this face in here. Okay, that face there and this face up here, all the same face. What we're going to do now is we're going to take our different heights. So we're going to take C, position for C, from the height that is. So from bottom line here, what height is C up? That's this one, marking that up, that's C. Going to do the same thing from B. Now remember, the face stops here, it does not go over to here, our face stops here. So it's from this point so that's point D here, and this line coming across is the line CD. Point A is quite easy to find as it is on the top surface, top edge, so we can just project that up. This is A up here. And to get B, we need to use our axonometric view. So we can't measure the distance here. That won't work because it's foreshortened. What we're going to do is we're going to take B. So in the past, we've been able to take points from here up into the elevation, into the axonometric view. We're going to take them from the axonometric view down into the plan, or back to the plan. So we're going to take this point down here. This is the bottom edge down here. B is on the bottom edge down there, so that would be this point on the bottom, just like it is there. And now I can project that from my plan into the auxiliary elevation. This giving me point B. Joining up A to B. And the angle, determine the true angle between the lines AB and CD. This here is the true angle, or that there's the true angle. So that completes this question, 2017 higher level section A1. Question A2 is a conics question. So the graphic below shows a logo for the Ladies Professional Golf Association. Contains a combination of geometric curves depicting a female golfer. The main curve is a parabola and the golf shaft is a normal to the parabola. The drawing on the right shows the axis A1, which is going to be this line coming along here, the directrix D1, this line here, and the focus F of a similar parabola. So this is our focus. Part A, this question is to locate the vertex and draw a portion of the parabola. Part B is locate a point P on the curve, which is 30 millimeters from the directrix, and construct a normal to the curve at point P. So for this, we're going to need to use our eccentricity line. So eccentricity for a parabola is always 1. So from where our axis intersects the directrix, we can take a line at 45 degrees. Our line of 45 degrees gives us a ratio of 1, so the distance from focal point to any point in the eccentricity back to D is the same distance. So from here to here will be the same as there. So it's from there up to here and back is the same distance. So our directrix here is at 45 degrees. What we're going to do next is we can draw a vertical line through the focus, above and below the line. So when it says draw a portion of the parabola, that generally means either side of the axis, top and bottom, because our parabola extends on. So we're just drawing this visible part of it. First thing we need to do is locate the vertex. So the vertex is always found, and this applies to all our conics. If you take a line at 45 degrees from the focus until it hits our eccentricity line, and then bring that back down perpendicular to our axis, this point here is our vertex. Okay, so taking this line here, 45 degrees, until it hits the eccentricity line and back down, gives us that point. What we're going to do now is going to divide this up into a couple of different sections. So generally you need maybe 5 points, and it's best to mix 5 up between outside the focal point and between the focal point and the vertex. So it's always best to include a couple there. So to make things a bit clearer, I've just made this line going through the focus blue, so that'll help us because we'll need to use that line. So what we're going to do, the first point anyway that we have on the curve is this one here. Okay, so that's kind of our second point. We have the vertex and we have this point. So a line through the focus that's perpendicular to the axis, where that cuts the eccentricity line, that's a point on the curve. What we're going to do from each of the other points then, so if we take this point up here, I'm going to go from that there, just random lines drawn until it cuts the eccentricity line, parallel to the axis, back to our blue line, which is this point. I'm going to use my compass on the focal point and rotate that back down until it cuts the original line, so cutting this one here. Same thing for the next one in, so this line hits the eccentricity line back into our blue line, rotate it around the focal point, so from here back down, that gives us this point here. Next one, so we have that point, this point here is the same, and as I'm at it, it would make more sense to do that distance, mark the same distance on the other side. So for here, so again, horizontal or line parallel to the axis from where this division line hits the eccentricity line, and then I'm going to rotate this back until it hits the bottom line. So that hits here, another point on the curve, do the same point below that one. So just repeating this. Another point, and just matching the last two, which I missed a while ago. So that gives us a number of points, and we can join all of these up together. Best curve that we can. that is the first part of this, locating the vertex and drawing a portion of the parabola. So for part B of this question, we're asked to locate a point P on the curve, which is 30 millimeters from the directrix, and construct a normal to the curve at point P. So to get a point that's 30 millimeters away from the directrix, we're going to need to draw a line parallel to the directrix from, so just measuring out 30 millimeters, drawing a line parallel to it. So that's going to give me this point here, this point on the curve that's 30 millimeters away. So what we're going to do from here, here's the point, that's the point, we're asked to draw a normal. So a normal is a line that's perpendicular to a tangent, so the constructions for this are going to be pretty much the same as if we were drawing a tangent until the very last step. So what we're going to do is we're going to join, I'm going to do this in red, join the focal point to the point on the curve, so from here to here. So that's the focal point on the curve. So just for all conics, how you find a tangent is you join the point, this point up here, to the focal points and bisect the angle that's formed between them. This applies to all conics. It applies to the ellipse and to the hyperbola. You join lines to the focal points, bisect the angle that's formed between them. The parabola has one focal point that's accessible. The other focal point is way off at infinity. So how that's going to appear is that's going to appear as a horizontal or a line parallel to the axis. So if I'm coming from point P, a line parallel, this line here is parallel to this one. So our normal is going to be halfway between this red line and this red line. So all we're going to do now is if we just bisect that angle, bisecting the angle and the remaining line that's formed. So joining a line from P through that, out the other side, that is the normal to complete this question.